Right, the fact that I've started again is a clue that I didn't do a very good job of explaining it first time around, so I'm having another go. So this question is really quite hard, so don't worry if you didn't get it right. It's pretty hard to explain. I managed to get it right first time, but not in a way that I could explain very well, so I'm having another go now. So you've got a hydrocarbon, CXHY, reacting with oxygen to give you carbon dioxide and liquid water. And you're asked to sort of figure some stuff out from it. So let's just think about what we know to start with. And the way that it's covered in the explanation, all I'm thinking is probably the best way to tackle this, I suppose. So if you've got a hydrocarbon, it's only got carbon and hydrogen in it. However many atoms of hydrogen, however many atoms of carbon are in this hydrocarbon, must be that many molecules of carbon dioxide, because there's one carbon per carbon dioxide molecule. Okay. Other thing that's relatively straightforward is that however many atoms of hydrogen there are in the hydrocarbon, must be half as many molecules of water, because there are 2 hydrogen atoms per molecule of water, so you're going to get half as many moles of water as you've got atoms of hydrogen, right? The slightly more awkward thing to figure out is the number of moles, or the ratio of moles of oxygen. I think that's the trickiest bit of this question, actually. But it must be that you get the oxygen that ends up in the carbon dioxide must be X lots of those, because there's O2 in carbon dioxide, so X lots of those. And there must be Y over 4, and I think this is the hardest thing to explain, must be Y over 4 molecules of oxygen as well as the ones that we use to make carbon dioxide. And that's because we've got Y over 2 moles of water, but you only need 1 oxygen atom per water molecule, but each oxygen atom has got, each oxygen molecule is 2. So that's the slightly tricky thing. There is another approach to it, which is quite hard to explain. But I think if you start with that, after that it's relatively straightforward. So you're told the initial initial volume of the hydrocarbon, and you're told you're starting with 1,000 centimeters cubed of the oxygen, and then you end up with 750, which I'm going to make a note over there, 750 centimeters cubed of gas. What it tells you is that if you take that product gas, which is, all of this has been used up, because it tells you that, so used up, it's 100, so there's none of that left, remaining 0. We're told that there's 750 left, which must be the excess oxygen plus the carbon dioxide. The water's a liquid, so we can ignore that. The chemistry that you probably won't know unless you looked it up is that if you take carbon dioxide gas and shake it with sodium hydroxide, it reacts, it's gone. The carbon dioxide disappears. So you can work out how many centimeters cubed of carbon dioxide there were by doing 750 take away 350. So used were none. So let's call this the change. So it's minus 100. 400 centimeters cubed of carbon dioxide produced, so remain with 400 there, which is eventually taken out of the reaction with the sodium hydroxide. So we must have used, using that number there, we must have used up in the chemical reaction 650 centimeters cubed of oxygen, because we were left with 350 centimeters cubed of oxygen at the end. Okay, so remaining 350. The key, the important row is this one. This tells you about the molar ratios. So the molar ratio of the hydrocarbon to carbon dioxide is 1 to 4. Okay, so X is equal to 4 then. And we know, don't we, that there is a 1, where is it? 1 to 6.5 ratio. I should have put the ratios in that we know. So there's a 1 to 6.5 to 4 ratio. X is equal to 4. This value here, so X plus Y divided by 4 is equal to 6.5. If you work that out, that means that Y is equal to 10. Because if you do, just prove that too if you want me to, Y divided by 4 is equal to 6.5 take away 4, which is 2.5. Do 4 times 2.5 is equal to 10. So Y is equal to 10. So X, Y is is that. You can start working out below if you're really interested. All right, there we go. That's that one I'll do. That is a very, very hard question. That's my other hacked attempt at trying to explain it. Right, so question 6. And for this one, this is a fairly common sort of a question that it's going to use the ideal gas relationship when you're comparing it before and after with the gas. So P1 V1 over T1 is equal to P2 V2 over T2. Now it's worth remembering you've got to convert Kelvin temperature into Kelvin. So if I just write down the numbers, so pressure 1 is equal to 99.3, temperature 1 is equal to 22 add 273, so 295, and V1 is just given to you as 49.6, P2 101.2, T2 is equal to 298, and V1 is what we're trying to figure out. V2 is what we're trying to figure out. So we rearrange this equation. V2 is equal to P1 V1 over T1 times T2 over P2. It's just this equation rearranged, and that hopefully is that. Yeah, just pause the video to check that is right. So this is the first pressure, second pressure, and that's T2, and that's T1, and that's the volume, so that is right. Okay. So very common they ask this question. Question 7. Assuming the volume is additive, what's the concentration of sodium hydroxide in the resulting solution? Okay. So let's work out the number of moles, shall we? If in doubt, work out the number of moles. So we've got 300 centimeters cubed to the volume of 300 centimeters cubed, which is equal to 0.3 decimeters cubed. Maybe worth making a note of. We've got concentration 0.5. So N is equal to C times V, which is 0.3 times 0.5, so half of 0.3, which is 0.15. The number of moles from there, we've got 200 centimeters cubed of 0.4. So the volume is 0.2 decimeters cubed. Concentration is 0.4. 0.2 times 0.4 is a fifth of 0.4, is 0.08 moles, and we've got to work out the new number. So the total number of moles then, just sodium hydroxide. Total number of moles is 0.23 for the sodium hydroxide, and the total volume is 0.5. It's 0.3 and 0.2. So we've got in 1 decimeter cubed, then we'd have 0.46. Okay, because one decimeter cubed is twice that, so 0.46. Concentration is 0.46 moles per decimeter cubed. So that's none of those answers. So maybe we have to convert to grams per decimeter cubed. Sodium hydroxide's got a molar mass of 40, and so the MR of sodium hydroxide is 40, which it is, and so concentration in grams per decimeter cubed is 0.46 times 40, which is 18.4 grams per decimeter cubed. Okay, that one. Question 8. Hydrogen and oxygen reacting to form water. So let's write out the equation. Emphasising the state 6 is talking about volumes, isn't it? So let's make a note of the ratio to start with. 2 to 1 to 2. The volume of gas, the same temperature and pressure. We've got 5.8 of hydrogen. All of the hydrogen is used up. What's the minimum volume of oxygen required? Okay, so we divide that by 2 because it's 2 to 1 ratio, so the minimum volume must be 2.9. I don't think I missed anything. Missed anything, just checking, make sure I've got the right answer. I've literally no idea whether I've recorded any of what I've just said. This question was relatively straightforward. It's a 2 to 1 to 2 ratio here. You start with 5.8, so it's a 2 to 1 ratio. Divided by 2, it's 2.9. That's that one. If you need me to go back over question 7, there's my working out. You can pause it and have a look at that. If you want me to go through that again because I've forgotten to record it, or I've hit pause or something, let me know. Okay, so I've made a bit of a hash of this video then, haven't I? So question 9, I'm going to plough on anyway. Question 9, atom economy questions are relatively straightforward. Hopefully that wasn't too much bother. You're given the balanced equation. What's slightly annoying though is they've tried to throw you by giving you a value of 100 grams. So it's only about atom economy, which is a function of the equation. It's got nothing to do with the amount of stuff you've got. So that 100 is really not helping you there. Okay, so we've got 2 lots of ethanol produced. We've got 2 lots of 46 divided by the total of all of the reactants or all of the products, whichever, and you're told that that's 180. So it's 180 times by 100. Do that one. Atom economy is a routine skill that you need to be able to do. The next question is percentage yield. You're told you've got, again, a pretty routine question, I'd have thought. Let's just do it. You've got 14 grams of ethene. You get 86.4 grams of 1,2-dibromoethane. So let's work it through. We've got C2H4. I'm going to try and squeeze it under here. It's a 1 to 1 to 1 ratio. And I've got 14 grams of ethene. I can work out the number of moles quite quickly, can't I? So 14 divided by 28, which is 0.5. So I should, if I've got a high yield, get 0.5 of this stuff. But I only get 86.4 grams. If I've generated 0.5 moles of that stuff, and the MR is 188, I can work out the mass. So the mass of the product you'd expect to get, mass equals MR times moles, so 188 times 0.5. So the expected mass is half of that, so that's 94, isn't it? You expect to get 94, and so the percentage yield is the mass produced, which is 84.6 divided by 94 times by 100 is equal to whatever. So you've got a couple of choices here, and these questions in here, they came from the fact that it used to be multiple choice without a calculator. From your course, you do not have the restriction of not having a calculator anymore, so it's unlikely they're going to give you these sorts of questions now. But you can just tap away and do it the way you've been taught up to this point, and you'll find, if I've done that right, which I think I have, question D gives you the right answer there. Okay, you should find that it matches up with what you've done. Okay, I'm just going to move on. Question 11. What's the maximum volume of hydrogen evolved when a piece of zinc? Again, this is a fairly sort of routine question, I would say. You've got some zinc. As long as you can do the balanced equation, you should have looked this up if you couldn't do it. Zinc forms a 2 plus ion, which is one of the things I asked you to learn at the start of the year. So that will be the balanced equation. And metal plus acid gives you salt plus hydrogen. Again, one of the reactions I asked you to learn at the start of the year. That's solid, that's aqueous, and that's a gas. You're asked about how much hydrogen is produced. Okay, you're told you've got 3.269 grams of zinc. And you're told the volume and the concentration of some hydrochloric acid. The volume is 75, and that's 1. And I'm just going to work out the number of moles and pause. Well, zinc's got a formula mass of 65.38, so mass divided by the MR is, so this number divided by this number is 0.0 0.5 moles of 0.05 moles of zinc, and we've got 7.5 or 75 sorry times by 1 divided by 1000 is equal to 0.075 moles of this stuff. So I have to work out which one is in excess and which one's the limiting one. More importantly, if we've got 0.05 moles of zinc, we would need twice as much of that, so 0.1 moles of HCl. We don't have enough of it, so that must be the limiting one. That's in excess. We've got more zinc than we have got acids that can react with it. So the relationship is between this and this. So it's 0.075 divided by 2, which is 0.0375 moles of that stuff. And then we're going to multiply that by the molar volume of gas at standard temperature and pressure. So the volume is equal to 0.0375 times by 22700, and that comes to that number A. Question 12. This is an N equals CV question, isn't it? Let's turn that into decimeters cubed, 0.2 decimeters cubed. The number of moles is 0.025 times 0.2. Plug it into your calculator. And it comes to 0.005, which is this one. Okay, should be a relatively straightforward one. Question 13. A titration question, really. So we've got to realise that these are different types of acid. We've got diprotic acid and monoprotic acid. So the key thing we need is to work out how many moles of sodium hydroxide we've got to start with, which is again N equals CV divided by 1000 because it's in centimeters cubed. So 25 times 0.16 divided by 1000. So we've got 0.004 moles of KOH. Alright, so if it was monoprotic acid, you'd need 0.004 moles of the acid. If it's a diprotic acid, you need half as much, you need 0.002 moles. Okay, so now tapping it into the calculator to see which one of those is the right one. So we'll start with A. So volume is 12.5 times 0.16 divided by 1000, and it comes to 0.002 moles. There's no point looking any further because that's the right answer, because if it wasn't clear, you need 2 sodium hydroxides for every 1 sulfuric acid, because sulfuric acid is a diprotic acid and we get this reaction going on. Okay, 1:2 ratio. We need 0.004 of this stuff, so we must need half the amount of this stuff, so that's the right answer. Feel free to plug into the other ones, but none of them will be right, I assume. Question 14. We've got which reaction will produce a theoretical volume of hydrogen gas. So this is really similar to what we just did a little bit before at the top here. So this reaction here, I'm only going to go straight to the right answer, which I know is B. For all of them, you have to work out what the balanced equation is. So for the top two, it's zinc plus H2SO4 goes to zinc sulfate plus H2, just a 1:1 ratio. The ones beneath, it's zinc plus 2 HCl, because zinc chloride is that. Okay, so it's a slightly different reaction. But all you've got to do is work out, first of all, how many moles of hydrogen gas that is. That is a gas. So we do 454 divided by the molar volume of gas, which is 22,700, which comes to 0.02 moles. So if in doubt, again, work out the number of moles. And then you've got to work out which one of these makes sense then. So one of these two, this one, it turns out, gives you the right answer. So if you look how to work that out, so if we've got 20 times 1 divided by 1,000 to work out the number of moles. We get 0.002. So both of those are 0.02 moles of sulfuric acid, which is the right number of moles of sulfuric acid to get that many moles of hydrogen. But one of them, you'll realise, has a limiting amount of zinc, and that's this one. If you work it through, the number of moles of zinc, 1 gram of zinc isn't enough to react with all of this sulfuric acid. So it's just a case of writing out the equation, writing out the number of moles. It's limiting reactants is what's going on with that one. Question 15 isn't a calculation question. It is just that one. I'm not going to go through that question now. Okay. Copper metal can be produced by reducing copper oxide with hydrogen. Okay, so that's a way that copper is made. So we've got copper 2 oxide. So again, try and work out what the equation is. React it with hydrogen will give you copper and water. Okay, it must be that. Okay, water is produced from the oxidation of the hydrogen, and the copper is reduced. Copper oxide is reduced. Okay. You're told you've got 100 grams, so the ratio, let's do it properly. Ratio 1 to 1 to 1 to 1. You're told you've got 100 grams of copper oxide. And you're told you've got 2.020 grams of hydrogen gas, and you're told you end up with 57.20 grams of copper. So which row must be correct there? Well, let's start off with the atom economy. I mean, it's clear we've got 2 products, so it can't be 100% atom economy. It must be either W or Z, right? Because it can't be 100% atom economy without even doing the sums. So let's work out the number of moles, as we always do. Copper oxide has got a formula mass of 63.5 at 16, roughly 79.5. And so 100 divided by 79.5 is 1.258 moles. Hydrogen's got a mass more or less of 2.02. We've got 1 mole of this stuff. So given it's a 1-to-1 ratio, it's easy to see this is an excess. This is the limiting reactant. And so we must produce 1 mole of copper. Copper has got a formula mass of 63.6. So this is that was the actual yield, wasn't it? The theoretical yield is 63.6 grams, right? And we can work out the percentage yield. It must be 90. It's that divided by that times 100. But yes, so D must be the right answer. Not D, but Z. What's the sum of the coefficients to balance this equation? Now, unfortunately, this is an unfortunate question because you've not done redox chemistry yet. So this is very easy to balance once you know what you're doing. So I'm afraid I'm just going to skip it because there's a technique to this which would make it very, very easy. You could have worked it out by trial and error. And I'm sorry if you spent a long time on this one. The answer is B20. But there's an approach to this which makes it very, very straightforward, which I'm just not going to try to cover now because I'm going to teach you that properly. I'm sorry it isn't a good question, it's really. Well done if you worked it out, I should say, as well. Okay, we've got another one, we've got another hydrocarbon question, so I'm going to make a pause and just write a little bit of it. Okay, so filled in the grid. So the starting volume of the hydrocarbon was 20. You're not told anything about the oxygen. The change in volume is how much is used up or how much is produced. So the hydrocarbon, all of it was used up. We ended up with none of that stuff. We started with no carbon dioxide or water. Remember here that water is a vapour, it tells you that, so we've got to write this as a gas. We gain 60 and gain 80. It's this, always this row here, the change that's going to give you the molar ratios. The molar ratios here or 1 to 3 to 4. Okay, so that tells you whatever x is here is the number of moles of this one. So that's straightforward. So C must be 3. That's the first one. That's easy to work out. The second part of it is always a bit trickier, because the ratio is 3 to 4. You produce 4 moles of water, but don't forget the water's got 2 hydrogens in, so it must be that this is 8. So the ratio, so this is, remember, this is y over 2. We covered that a little bit earlier on, because there's twice as many water molecules, half as many water molecules as there are hydrogens in here, because we need 2 hydrogens per water. So it's C3H8. Okay, that's that. So that one.